Hi, welcome back to my channel. I'm Henry, and so today we are going to study AP Calculus AP together. So, um, why I learned this? So, because in the future, I think 2 more years, I'll be traveling to the US to apply for universities and colleges. And so, my dream is to be a computer engineer. So it's not so it's obvious that I have to learn physics, maths, and programming. So stop talking unnecessary things right here. So let's dive into the problem. So now, in this video, I'm going to study with you guys AP calculus AB for limits and continuity. We learned two lessons today. So the first lesson is limits by direct substitution and direct substitution with limits that don't exist. Okay, so I assume that this video will take around 45 or 46 minutes or maybe more. So please consider watching this video, or you can leave this video right here because this is going to be a bit long. Okay, so let's dive into lessons. First thing we are going to learn today is limits by direct substitution. So obviously we watch video.
So let's see if we can find the limit as x approaches -1 of 6x squared plus 5x minus 1.
Wait a little bit, so let me write down some information for my notebooks. Right. So let's keep going.
Now, the first thing that might jump out at you is this right over here. This expression could be used to define the graph of a parabola. And when you think about this, I'm not doing a rigorous proof here. A parabola would look something like this, and this would be an upward opening parabola. Looks something like this. It is this graph visually is continuous. You don't see any jumps or gaps in it. And in general, a quadratic like this is going to be defined for all values of x for all real numbers, and it's going to be continuous for all real numbers. And so if something is continuous for all real numbers, well, then the limit as x approaches some real number is going to be the same thing as just evaluating the expression at that real number. So what am I saying? I'm just going to say it another way. We know that some function is continuous at some x value, at x equals a, if and only if, all right, that is if and only if the limit as x approaches a of f of x is equal to f of a. So I didn't do a rigorous proof. Conceptually, not a big jump to say, okay, well, this is just a standard quadratic right over here. It's defined for all real numbers, and in fact, it's continuous for all real numbers. And so we know that this expression, it could define a continuous function. So that means that the limit as x approaches a for this expression is just the same thing as evaluating this expression at a. And in this case, our a is -1. So all I have to do is evaluate this at -1. This is going to be 6 times -1 squared plus 5 times -1 minus 1. So that's just 1. This is -5. So it's 6 minus 5 minus 1, which is equal to 0. And we are done.
All right, so about the lesson. So I think the the main point of this topic is just placing the A into this. But okay, so this doesn't look like so I'll do an example first. So this doesn't look like we can substitute substitute it 0, so we get 3 here and we get minus 15, so we might get -5 It's easy. So 2. Okay, so we get 12a plus with 13, we get 25. Results in 5. Minus 3, negative 3. So negative 3, but powered by 2 is 9. Plus with 3 is negative. Plus with negative equal, negative with negative equals a plus. Yeah. So 9 plus with 3 equals 12. 12 minus with 1 equals 11. So 5 here, we have 11 here. So 3 is 1. So 3 minus 25 equals minus 22, which results in negative 2. And as I've said, but I think we finished it all today. So 45 minutes is not that long. Let's continue. So the next thing we're going to learn is a defined limit prerecorded substitution. So let me write things on my notebook. So yes, let's wait. Alright, so I'm back. So let's watch the video together.
Let's see if we can figure out the limit of x over natural log of x as x approaches 1. And like always, pause this video and see if you can figure it out on your own. Well, we know from our limit properties, this is going to be the same thing as the limit as x approaches 1 of x over the limit as x approaches 1 of the natural log of x. Now, this top limit, the one I have in magenta, this is pretty straightforward. This, if we had the graph of y equals x, that would be continuous everywhere. It's defined for all real numbers and it's continuous at all real numbers. And so if it's continuous, the limit as x approaches 1 of x is just going to be this evaluated at x equals 1. So this is just going to be 1. We just put a 1 in for this x. So the numerator here would just evaluate to a 1. And then the denominator, natural log of x is not defined for all x's, and therefore it isn't continuous everywhere, but it is continuous at x equals 1. And since it is continuous at x equals 1, then the limit here is just going to be the natural log evaluated at x equals 1. So this is just going to be the natural log of 1, which of course is 0. E to the 0 power is 1. So this is all going to be equal to, if we just evaluate it, 1 over 0. And now we face a bit of a conundrum. 1 over 0 is not defined. If it was 0 over 0, we wouldn't necessarily be done yet. That's indeterminate form. As we will learn in the future, there are tools we can apply when we're trying to find limits and we evaluate it like this and we get 0 over 0. But 1 over 0, this is undefined, which tells us that this limit does not exist. So does not exist. And we are done.
Okay, so I think this video is still like replacing things into the expression. This time, limit does not exist. So yeah, so let's do the exercise. So now the 5 here. Okay, so 5 is 5. Wait. Okay, so I'm back, and I think we don't really need to do some mathematic progresses. Just I need to replace things with 5 and x. So yeah, I calculated it. It's 7. So about this math problems, so we just need to replace 2 here. So it's definitely 4 0, so it doesn't exist. And number 3, 6 minus 4 negative. And we have Negative 5 plus root 5 is 0, so it doesn't exist. Okay, so I have the two exercises where you can learn new lessons. It's limits of trigonometric functions.
What we're going to do in this video is think about limits involving trigonometric functions. So let's just start with a fairly straightforward one. Let's find the limit as x approaches pi of sine of x. Pause the video and see if you can figure this out. Well, with both sine of x and cosine of x, they're defined for all real numbers. So their domain is all real numbers. You can put any real number in here for x, and it will give you an output. It is defined. And they are also continuous over their entire domain. In fact, all of the trigonometric functions are continuous over their entire domain. And so for sine of x, because it's continuous and is defined at sine of pi, we would say that this is the same thing as sine of pi. And sine of pi, you might already know, is equal to 0. And we could do a similar exercise with cosine of x. So if I were to say, what's the limit as x approaches, I'll just take an arbitrary angle, x approaches pi over 4 of cosine of x. Well, once again, cosine of x is defined for all real numbers. X can be any real number. It's also continuous. So for cosine of x, this limit is just going to be cosine of pi over 4. And that is going to be equal to square root of 2 over 2. This is one of those useful angles to know the sine and cosine of. If you think in degrees, this is a 45-degree angle. And in general, if I'm dealing with a sine or a cosine, the limit as x approaches a of sine of x is equal to sine of a. Once again, this is going to be true for any real number a. And I can make a similar statement about cosine of x. Limit as x approaches a of cosine of x is equal to cosine of a. Now, I've been saying it over and over. That's because both of their domains are all real numbers. They are defined for all real numbers that you put in, and they're continuous on their entire domain. But now let's do slightly more involved trigonometric functions, or ones that aren't defined for all real numbers, that their domains are constrained just a little bit more. So let's say if we were to take the limit as x approaches pi of tangent of x. What is this going to be equal to? Well, this is the same thing as the limit as x approaches pi. Tangent of x is sine of x over cosine of x. And so both of these are defined for pi. And so we could just substitute pi in, and we just want to ensure that we don't get a 0 in the denominator, because that would make it undefined. So we get sine of pi over cosine of pi, which is equal to 0 over -1, which is completely fine. If it was -1 over 0, we'd be in trouble. But this is just going to be equal to 0. So that works out. But if I were to ask you, what is the limit as x approaches pi over 2 of tangent of x? Pause the video and try to work that out. Well, think about it. This is the limit as x approaches pi over 2 of sine of x over cosine of x. Now, sine of pi over 2 is 1, but cosine of pi over 2 is 0. So if you were to just substitute it in, this would give you 1 over 0. And one way to think about it is pi over 2 is not in the domain of tangent of x. And so this limit actually turns out it doesn't exist. In general, if we're dealing with sine, cosine, tangent, or cosecant, secant, or cotangent, if we're taking a limit to a point that is in their domain, then the value of the limit is going to be the same thing as the value of the function at that point. If you're taking a limit to a point that's not in their domain, there's a good chance that we're not going to have a limit. So here, there is no limit. And a way to deduce that is that pi over 2 is not in tangent of x's domain. If you were to graph tan of x, you would see a vertical asymptote at pi over 2. Let's do one more of these. So let's say the limit as x approaches pi of cotangent of x. Pause the video and see if you can figure out what that's going to be. Well, one way to think about it, cotangent of x, it's 1 over tangent of x. It's cosine of x over sine of x. That's a limit. This is a limit as x approaches pi of this. And is pi in the domain of cotangent of x? Well, no. If you were to just substitute pi in, you're going to get negative 1 over 0. And so that is not in the domain of cotangent of x. If you were to plot it, you would see a vertical asymptote right over there. And so we have no limit. We have no limit. So once again, this is not in the domain of that. And so good chance that we have no limit. When the thing we're taking the limit to is in the domain of the trigonometric function, we're going to have a defined limit. And sine and cosine in particular are defined for all real numbers, and they're continuous over all real numbers. So you take the limit to anything for them, it's going to be defined, and it's going to be the value of the function at that point.
Alright, so the lesson is pretty easy. You just need to replace x in your calculator. Just apply formulas to calculate. So let's do the exercise together. Just for questions. So yes, pi k with 10 degree. So and yeah, I remember he chose 0 in this video. Okay, so second I really don't know. Let me try to search Google for a little bit because I never seen this before. Alright, guys. Alright, so let's watch the video together.
Let's think a little bit about limits of piecewise functions that are defined algebraically, like our f of x right over here. Pause this video and see if you can figure out what these various limits would be. Some of them are one-sided and some of them are regular limits or two-sided limits. All right, let's start with this first one. The limit as x approaches 4 from values larger than equaling 4. So that's what that plus tells us. And so when x is greater than 4, our f of x is equal to square root of x. So as we are approaching 4 from the right, we are really thinking about this part of the function. And so this is going to be equal to the square root of 4. Even though right at 4, our f of x is equal to this, we are approaching from values greater than 4. We're approaching from the right. So we would use this part of our function definition. And so this is going to be equal to 2. Now, what about our limit of f of x as we approach 4 from the left? Well, then we would use this part of our function definition. And so this is going to be equal to 4 plus 2 over 4 minus 1, which is equal to 6 over 3, which is equal to 2. And so if we want to say what is the limit of f of x as x approaches 4? Well, this is a good scenario here because from both the left and the right, as we approach x equals 4, we're approaching the same value. And we know that in order for the two-sided limit to have a limit, you have to be approaching the same thing from the right and the left. And we are, and so this is going to be equal to 2. Now, what's the limit as x approaches 2 of f of x? Well, as x approaches 2, we are going to be completely in this scenario right over here. Now, interesting things do happen at x equals 1 here. Our denominator goes to 0. But at x equals 2, this part of the curve is going to be continuous. So we can just substitute the value. It's going to be 2 plus 2 over 2 minus 1, which is 4 over 1, which is equal to 4. Let's do another example. So we have another piecewise function. And so let's pause our video and figure out these things. All right, now let's do this together. So what's the limit as x approaches negative 1 from the right? So if we're approaching from the right, when we are greater than or equal to negative 1, we are in this part of our piecewise function. And so we would say this is going to approach, this is going to be 2 to the negative 1 power, which is equal to 1/2. What about if we're approaching from the left? Well, if we're approaching from the left, we're in this scenario right over here. We're to the left of x equals negative 1. And so this is going to be equal to the sine, because we're in this case for our piecewise function, of negative 1 plus 1, which is the sine of 0, which is equal to 0. Now, what's the two-sided limit as x approaches negative 1 of g of x? Well, we're approaching two different values as we approach from the right and as we approach from the left. And if our one-sided limits aren't approaching the same value, well, then this limit does not exist. Does not exist. And what's the limit of g of x as x approaches 0 from the right? Well, if we're talking about approaching 0 from the right, we are going to be in this case right over here. 0 is definitely in this interval. And over this interval, this right over here is going to be continuous. And so we can just substitute x equals 0 there. So it's going to be 2 to the 0, which is indeed equal to 1. And we're done.
Alright, so to do this exercise, we are going to check the conditions here. Okay, so to ask any conditions here, just need to replace the number in the correct expression. Okay, so I'm gonna do an exercise so we can practice together. So first thing, the x is pi plus, so larger than pi. Okay, so it's asking this. So sine of pi is okay, it's 0. Okay, so we're asking is 5. Negative 5. So for negative 5, yes, we can see that the range is right there. So from 0 to negative 8, between them is negative 5. We can say negative 5 is between 0 and 10. So we're gonna place the number negative 5 first. So the sign of the multiplication between negative 5 with pi is still 0. Okay, so now we're gonna go to the next question. So now we can say 6. So 6 is between here, 6 and 10. Why is it? So we can't see. We can see there's like this layer bar. I don't know, like the layer bar here. So it's like smaller or equal to 6. So 6 is definitely equal to 6. So we're gonna go for these options. The cosine of 6 pi is equal to 1. Okay, so let's see. So the cosine of 6 is multiplied with this 1. Um, okay, so there's a case that both 6 minus 6 actually equal the limit of this. So we check. So for the so far the 6 on 3 minus 2, so it's 0, so 0 is definitely not equal to 1. Okay, so we can conclude that this limit doesn't exist. So if I paste, okay, so I'm gonna reset this because I want a really like a full correct performance. Alright, so we reached the last question, which I've redid it. Okay, so now we have this one x approaches -1 and -1, and we have two sides. So this is the right side, this is the left side. So we're gonna compare one one on -1 it equals to -1, and so I'm gonna note that. So it's -1, and for -1 this. So we're gonna add -1 to the multiplication between 2 and dx. So we're gonna have 1 plus with 2 multiplied -1 equals to -1. So we can see that the right side and the left side of the x approaches -1 is equal to the limit of the g of x when x approaches -1. So we say that the limit of the g of x at x approaches -1 is also equals to -1. So we're gonna choose A as an answer. Okay, we have done exercises. Let's watch the last video or this video. Limits.
Let's say that f of x is equal to the absolute value of x minus 3 over x minus 3. And what I'm curious about is the limit of f of x, as x approaches 3. And just from an inspection, you can see that the function is not defined when x is equal to 3. You get 0 over 0, it's not defined. So to answer this question, let's try to rewrite the same exact function definition slightly differently. So let's say f of x is going to be equal to, and I'm going to think of two cases. I'm going to think of the case when x is greater than 3 and when x is less than 3. So when x is, do this in two different colors actually. When x, green, when x is greater than 3, what does this function simplify to? Well, whatever I get up here, I'm going to get a positive value up here, and then when I take the absolute value, it's going to be the exact same thing. So for x is greater than 3, this is going to be the exact same thing as x minus 3 over x minus 3. Because if x is greater than 3, the numerator is going to be positive. You take the absolute value of that, you're not going to change its value. So you get this right over here. Or if we were to rewrite it, this is equal to, for x is greater than 3, you're going to have f of x is equal to 1 for x is greater than 3. Similarly, let's think about what happens when x is less than 3. When x is less than 3, well, x minus 3 is going to be a negative number. When you take the absolute value of that, you're essentially negating it. So it's going to be the negative of x minus 3 over x minus 3. Or if you were to simplify these two things for any value, as long as x does not equal 3, this part right over here simplifies to 1, so you're left with a negative 1. Negative 1 for x is less than 3. I encourage you, if you don't believe what I just said, try it out with some numbers. Try out some numbers 3.1, 3.001, 3.5, 4, 7, any number greater than 3, you're going to get 1. You're going to get the same thing divided by the same thing. And try values for x less than 3. You're going to get negative 1 no matter what you try. So let's visualize this function now. So now let me draw some axes. That's my x-axis. And then this is my f of x axis. Y is equal to f of x. And what we care about is x is equal to 3. So x is equal to 1, 2, 3, 4, 5. We could keep going. And let's say this is positive 1, 2. So that's y is equal to 1. This is y is equal to negative 1 and negative 2, and we can keep going. So this way that we've rewritten the function is the exact same function as this. We've just written it a different way. And so what we're saying is our function is undefined at 3, but if our x's are greater than 3, our function is equal to 1. So if our x is greater than 3, our function is equal to 1. So it looks like that, and it's undefined at 3. And if x is less than 3, our function is equal to negative 1. So it looks like, let me do that same color. It looks like this. It looks like this. Once again, it's undefined at 3. So it looks like that. So now let's try to answer our question. What is the limit as x approaches 3? Well, let's think about the limit as x approaches 3 from the negative direction, from values less than 3. So let's think about first the limit as x approaches 3, the limit of f of x as x approaches 3 from the negative direction. And all this notation here, I wrote this negative as a superscript right after the 3 says, let's think about the limit as we're approaching, make this clear. Let's think about the limit as we're approaching from the left. So in this case, if we get closer, if we start with values lower than 3, as we get closer and closer and closer, so say we start at 0, the f of x is equal to negative 1. We go to 1, f of x is equal to negative 1. We go to 2, f of x is equal to negative 1. If you go to 2.999999, f of x is equal to negative 1. So it looks like it is approaching negative 1 if you approach from the left-hand side. Now let's think about the limit of f of x, as x approaches 3 from the positive direction, from values greater than 3. So here we see when x is equal to 5, f of x is equal to 1. When x is equal to 4, f of x is equal to 1. When x is equal to 3.0000001, f of x is equal to 1. So it seems to be approaching positive 1. So now we have something strange. We seem to be approaching a different value when we approach from the left than when we approach from the right. And if we're approaching two different values, then the limit does not exist. So this limit right over here does not exist. Or another way of saying it, the limit of, let me write this in a new color. I have a little idea here. The limit of a function f of x as x approaches some value c is equal to L if and only if the limit of f of x as x approaches c from the negative direction is equal to the limit of f of x as x approaches c from the positive direction, which is equal to L. This did not happen here. The limit when we approached from the left was negative 1. The limit when we approached from the right was positive 1. So we did not get the same limits when we approached from either side. So the limit does not exist in this case.
Okay, so the problem of this topic of the problem of this is we need to consider the conditions of the x that approaches 3 here. We can say approaches c, so we should consider that x what is what's the result of the f of x if x is larger than 3 and x is smaller than 3, and if it returns the same result, then yeah, it continues and the limit does exist. But if it's not exist, then yeah, vice versa, it doesn't exist, like he said. Okay, so I think it's been like, okay, it's been like more than half an hour, so it's not really close to 45 minutes, and the lesson is pretty fast. Okay, so I hope you enjoy my video, and I hope you learned something meaningful, and maybe can help you to study AP calculus better. Okay, so I hope you have a great day, and have learned calculus AB well. Bye.